Hello and welcome back to the Science of Concrete Materials class. This is lecture number 36 of the class, and today we will start on the new module, which is the dimensional stability and the time-dependent deformations. These are the topics we are going to discuss in this module of the class. First, we're going to have some introduction generally about the time-dependent deformations. We will talk about drying shrinkage, carbonation shrinkage, autogenous shrinkage, creep, and thermal shrinkage. As we have been probably emphasizing or mentioning throughout the class, concrete will undergo volume changes while in service due to factors such as applied stress, change of moisture content, and changes in temperature. The response of concrete to these factors is really complex and will result in reversible and irreversible and also time-dependent deformations. In this part of the class, as I said, we will discuss two main types of deformation. First is shrinkage, which basically occurs with loss of moisture or some chemical processes, such as carbonation. The second will be creep, which is the time-dependent deformation that occurs on the prolonged application of stress, which is otherwise referred to as viscoelastic strains. The stress effects resulting from the drying shrinkage and the viscoelastic strains in concrete are not the same. However, with both phenomena, the underlying causes and the controlling factors have much in common. Important parameters that influence the drying shrinkage and creep will be discussed, such as aggregate content, stiffness, water content, cement content, time of exposure, relative humidity, and the size and shape of the concrete member. As a reminder though, concrete shows elastic as well as inelastic strains on loading, and the shrinkage strains on drying or cooling. So when restrained, shrinkage strains result in complex stress patterns that often lead to cracking if not really addressed properly during the design and construction. So the aim is to understand and try to prevent cracking resulting from these phenomena. By making sure we understand how they work and address whatever factors that we can during either the design of the concrete members or during the construction. In previous lectures, causes of the non-linearity in the stress-strain relation of concrete were discussed, if you remember, and the different types of the elastic moduli and the methods of determining them were also described. Explanations were provided as to why and how the aggregate, the cement paste, the interfacial zone, transition zone that is, and the testing parameters affect the modulus of elasticity. If you recall, such information are important as background for these common lectures. Okay. Also, the discussion related to the cement hydration and the hydrated cement paste microstructure also relevant. So the audience is advised to refer back to those lectures just to refresh your information and knowledge about the subject. Okay? So let's start with the drying shrinkage. The term drying shrinkage is generally reserved for hardened concrete. It represents the strain caused by the loss of moisture or water from the hardened material. We have, on the other hand, the autogenous shrinkage, which occurs when a concrete can self-desiccate. If you recall back to the hydration lectures, can self-desiccate during hydration. This is a special case of drying shrinkage. Also, carbonation shrinkage, which occurs, when hydrated cement reacts with the atmospheric carbon dioxide, also can be considered a special case of drying shrinkage. Okay? One thing also to emphasize, shrinkage is a paste property. In concrete, typically the aggregate has a restraining influence on the volume changes that will take place within the paste. Okay? Drying shrinkage of hardened concrete is a much more important phenomenon than those already described, the other two types. So inadequate allowance for the effects of drying shrinkage in concrete design and construction can lead to cracking or warping of elements of the structure due to restraints present, during shrinkage. Okay? So the most obvious example is the necessity of providing contraction joints in pavements and slabs. All right? So these joints prevent random, irregular shrinkage cracking and confine it to a desired location in the form, in which the crack can readily be filled with a sealant to prevent the entry of foreign materials. Okay? The response of the paste to moisture loss is modified by the presence of the aggregates and the shape of the concrete member. So even with good jointing, uneven shrinkage caused by moisture loss only from the top of a slab, for example, can cause curling at the edges. So that's something you have to be aware of. So to understand precisely how different experimental parameters affect the drying shrinkage of concrete, a study of hardened cement paste itself is appropriate. The factors that affect shrinkage are listed in the table on the next slide. I'm going to show just in a minute here. Here it is. As you can see here. Okay? So these are basically the parameters that will affect shrinkage. A lot of them. We have three categories. First, the paste parameters, which are related to the paste. Porosity and age of paste, which basically related to the water cement ratio and the degree of hydration, curing temperature, cement composition, moisture content, and the presence of admixtures or other additives. The concrete related parameters, the aggregate stiffness and content, volume to surface ratio, and the thickness of the member, since that will affect the rate of the moisture migration from the member to the surroundings. We have also the environmental parameters, the applied stress or duration of load. Of course, these two items basically affect creep. Relative humidity, which affects the rate of moisture loss from a member, rate of drying, and the time of drying. So all these items need to be thought of when we are trying to control the drying shrinkage, okay, and the creep eventually, as you will see. So let's look at the behavior of the cement paste. One thing that needs to be mentioned, that the results discussed and within this discussion are based on laboratory work using cement paste specimens with relatively small cross sections. Because if such specimens are not used, then the rate of diffusion of water from the specimen to the surroundings makes reaching equilibrium states difficult to achieve and will complicate the interpretation of the data. So one important aspect concerning the drying shrinkage of cement paste and eventually the concrete, is the fact that part of the total shrinkage that occurs on first drying is irreversible, as you can see here. Once the member undergoes drying, it will be subject to shrinkage. Now, let me go back. At re-wetting, we will not go back to the same state. So this part of the shrinkage is irreversible. So the subsequent, as I said, volume expansion that occur on re-wetting and volume contractions that occur on subsequent drying are smaller, as you can see from this graph here. So experimental parameters generally have some effect on the amount of irreversible shrinkage as well as on the total shrinkage. That's something we might touch upon later. And basically that since, moisture loss is the underlying cause for drying shrinkage, the relationship between the two should be of interest, as I will explain on the next slide, okay? As you can see on this figure, when basically shows a typical shrinkage weight loss curve for cement paste, in which we have observed 5 domains, 1 through 5, as you can see. Domain 1 is attributed to loss of water from large capillary pores, which are the macropores, if you remember the hydration, the cement paste microstructure lectures. We then, domain 2, right here, water is lost at the same time from both mesopores and the micropores, meaning water is lost from both the finer capillary pores and the intrinsic calcium silicate hydrate gel porosity. At the end of domain 2, right here, all water held in the pore system has been removed. Okay? During domains 3 and 4, water adsorbed on the solid surfaces is removed. Okay? So while basically in domain 4 also, the interlayer water of the calcium silicate hydrate is also removed. So all of this water can be removed at room temperature, evaporable water, or more likely around 105 Celsius, about 221 degrees Fahrenheit. Above this temperature, decomposition of the calcium silicate hydrate is responsible for the additional shrinkage, observed in domain 5. Okay? Also, shrinkage in domains 4 and 5 will only occur in concrete exposed to fire. Okay, as you can see from the range of temperature that the concrete has to be exposed to in order for this shrinkage to take place. All right? Okay, the closely related plot of shrinkage versus relative humidity in this figure here emphasizes the difference between the various domains I explained on the previous slide. Since in most civil engineering applications, concrete is really not exposed to very low relative humidities for extended period of times. So we need only to concern ourselves, with the behavior in the upper humidity range. Generally speaking, okay? In some cases, low humidity is possible, but I'm talking in general here, okay? So let's look at the mechanisms of shrinkage, mostly the reversible shrinkage. 3 phenomena are believed to contribute to bulk shrinkage of cement paste, which are, the capillary stress, denoted as P sub cap, the disjoining pressure, just P sub this right here, and the changes in surface free energy, P sub SFE. These phenomena result from the special nature of the hydrated cement paste. Basically, it's high porosity with a network of small capillary pores. So and also the extensive, van der Waals bonding in the calcium silicate hydrate gel, and the high surface area and the intrinsic microporosity of the calcium silicate hydrate. Okay, so the net linear shrinkage is a function of internal pressures developed by the capillary stresses, the P sub cap, the disjoining effects, and the changes in the surface free energy. Okay, although it is linear shrinkage that is usually measured experimentally, a volumetric contraction actually occurs. So, and also these, three phenomena, the capillary stress, disjoining pressure, and the change in surface free energy are dependent on both relative humidity and also the temperature. So let's look at each mechanism in detail to some extent. Let's look at the capillary stress. As we may have explained before, water within the small capillary pore is partially under the influence of the surface interactions exerted by the pore walls. So water cannot be removed by evaporation unless the relative humidity is lowered by an amount dependent on the radius, the pore radius that is, and given by this equation right here, which basically natural logarithm of the relative humidity equals to K, which is a constant, times 2 times gamma, which is the surface free energy, surface tension, divided by the pore radius. Okay? So the water can only be lost by the creation of an air-water interface or a meniscus. All right? Which requires energy. As a result of the interactions with the pore walls, the meniscus adopts a curved surface, as you can see right here. And the water in a state of hydrostatic tension, which is basically the capillary stress, which can, be expressed in this equation right here, okay? Which is 2 times gamma over R, the radius, and of course substituting from this equation equals natural logarithm of relative humidity over the constant K. Okay, so basically the water exerts a corresponding hydrostatic compression on the solid skeleton, and if internal particle rearrangement can occur, as the case of the for the cement paste, some pores as a result can become smaller, and this is what is schematically provided in this figure right here. Okay, how this the pore will get smaller, as you can see here. Okay, the second phenomena is the disjoining pressure. Basically, water is adsorbed on the surface of the calcium silicate hydrate layers at all relative humidities. So the thickness increasing with increasing humidity. An assembly of the colloidal particles, as in the case of the calcium silicate hydrate, has van der Waals forces attracting adjacent particles and bringing their adjacent surfaces in close contact. Okay? The adsorption of water between the calcium silicate hydrate surfaces creates disjoining pressure, which results, from the orientation of the water molecules in the adsorbed film. The disjoining pressure increases with the increasing thickness of the adsorbed water between the particles, meaning increase in relative humidity, until basically it exceeds the van der Waals attraction forces, okay? When the particles will be forced apart, creating basically a dilation. So the calcium silicate hydrate, formed in the dilated state during hydration, and the water-filled spaces are, the micropores. So on first drying, the decrease in disjoining pressure, which accompanies a lowered relative humidity, causes the particles to be drawn together, okay, by the van der Waals forces, and there is a net volume decrease, as you can see here, from between this case and this case right here, okay? So disjoining pressure is only a significant factor to about 45% relative humidity, okay? And it shows, a relative humidity dependency similar to capillary stress. That's what you need to remember, okay? So as you can see here, the mechanisms of the dilation, and then what happens when the relative humidity decreases and the volume contraction occurs. Okay, the third phenomena we talked about is the surface free energy, okay? So this is basically responsible for shrinkage below relative humidity of 45%. It's greatest about, or below 20%. As you know, most of the tightly held water is removed. The surface free energy of the calcium silicate hydrate gel grows, okay? A pressure is generated, proportional to the surface free energy and the surface area of the particles. And this pressure, will lead to compression of the solid, as you can see right here, okay? So let's talk about the irreversible shrinkage. As can be seen here from the figure to the right, which I talked about a few minutes ago, there is a considerable part of the observed length change on first drying is irreversible, which is this portion right here, okay? Although, as the mechanisms described above, the three mechanisms I just described, would predict reversible shrinkage, but still a portion of the shrinkage is irreversible. So the figure to the left here shows that irreversibility occurs only on first drying, and that the deformations subsequent on subsequent wetting and drying are essentially reversible, as you can see here. That's what happened at first drying, but after that, at wetting, on subsequent wetting and drying, the shrinkage is reversible, as you can see here. This is the part that is not reversible, okay? Okay, so irreversible shrinkage, as we said, is probably due to the development of chemical bonds within the calcium silicate hydrate structure, as a consequence of the drying. This leads to improvement in the dimensional stability of concrete as a result of first drying, okay? So the relative amounts of reversible and irreversible shrinkage are due to many factors, including the water-cement ratio, the cement composition, degree of hydration, the use of supplementary cementitious materials or chemical admixtures, curing history, temperature, relative humidity, and the drying history, okay? So these are the things you need to remember. Okay, let's talk about the factors that affect or influence the shrinkage. The first is the aggregate. The drying shrinkage of concrete will be less than that of pure paste because of the restraining influence of the aggregates. With rare exceptions, aggregates are dimensionally stable under changing moisture conditions, as we have established during the talk about the aggregates. Okay, so the amount of restraints provided by the aggregates depend on the amount of aggregates in the concrete. As you can see here on this figure here, on the top figure right here. Okay. Basically, this is the relative shrinkage, and as you see, there is a decrease, and this is the aggregate content. This is the range basically of the concrete, between 60 to 80% by volume are aggregates. Okay, so the stresses at the cement paste aggregate interface due to drying shrinkage increase as the maximum aggregate size increases. These higher internal stresses will increase the amount of cracking in the interfacial zone. Lightweight aggregates are generally dimensionally stable, but their modulus of elasticity, the low modulus of elasticity, means that lightweight concretes can be expected to have higher shrinkage than normal weight concrete. Okay, so they are dimensionally stable in general, but the shrinkage will be higher. The combined effects of aggregate content and stiffness are basically represented in this empirical equation right here. Okay, basically this is the represented by the Greek letter epsilon, which is, this is the concrete shrinkage strain, and this is the paste shrinkage strain, and V sub A is the volume fraction of aggregate, and the letter N, is a constant which varies between 1.2 to 1.7, depends on the elastic properties of the aggregate. So this is the predicted shrinkage strain of concrete based on the shrinkage strain of the paste and the volume of the aggregate. Okay, so again, it's a empirical formula, but nonetheless, it's there. So this basically the volume of the aggregate, and also the modulus of elasticity, or the stiffness of the aggregate, also influence the overall shrinkage or drying shrinkage of the concrete. Okay. The second factor that influences shrinkage is the specimen geometry. So the size and shape of a concrete specimen will determine the rate of moisture loss and eventually the rate and magnitude of drying shrinkage. The length of the diffusion path has a strong influence on the rate of moisture loss. So in mass concrete, it will take approximately 1 month for the outer 75 millimeters or 3 inches of concrete to reach moisture equilibrium. Maybe 1 year for 225 millimeters and about 10 years for 600 millimeters or 24 inches to reach equilibrium. So volume to surface area ratio will be important, and a higher ratio will lead to less shrinkage. So for example, a T-beam section will dry more rapidly than a square beam, but have less ultimate shrinkage. Okay, so the rate of moisture loss depends on the total surface area and the average length of the diffusion path. The smaller the initial cross section of a member, the faster the initial rate of shrinkage, but the lower the magnitude of shrinkage at later times. Similarly, with reduced surface areas, the lower rates of early shrinkage extrapolate basically to large ultimate shrinkage. So there is an inverse relationship between the rate of early shrinkage and the ultimate shrinkage. Okay? This is basically opposite to the effect observed for pastes. This apparent contradiction is in part due to the increased amount of hydration of the slower drying specimens, but it's primarily caused by the restrained shrinkage. Okay, as we said, drying shrinkage of concrete specimen during the drying of a concrete specimen, the situation soon arises where a dry contracting exterior surrounds a still moist core that has not begun to shrink, okay, as you can see in this figure right here. So the tensile stresses will basically will be set up in the outer part of the prism, the one you're looking at. And microcracking is likely to occur unless the stress is relieved by the tensile creep, as we will see later. So either creep or microcracking will act to reduce the observed shrinkage. So, and again, the moist core will be subject to a compressive stress under which, it will creep and may also affect the magnitude of later drying shrinkage. Okay? So this is just, I wanted to mention that just for completeness. Okay, let's look at the other type of shrinkage I mentioned at the beginning of the lecture, which is the autogenous shrinkage. Okay, if no additional water beyond that added during mixing is provided during curing, concrete will begin to dry internally, even if no moisture is lost from, to the surroundings, as water basically is consumed by hydration. However, bulk shrinkage is only observed in concretes with low water cement ratio, maybe below 3.3, and is increased by the addition, this shrinkage is increased by the addition of reactive pozzolans, especially silica fume. So the phenomenon is known as self-desiccation and it is manifested as autogenous shrinkage, also known as chemical shrinkage. In extreme cases, the internal relative humidity can drop to maybe 75 to 80%, to 75 to 80, between 75 and 80%, the internal relative humidity. So this shrinkage is basically a special case of drying shrinkage, and it is also of similar magnitude. Since really it is immaterial whether the water is removed by physical or chemical processes, so it is a special case of drying shrinkage. Autogenous shrinkage will only occur if the concrete is sealed or it is in the cases of dense concrete, meaning low water cement ratio and the additions of silica fumes, as I will show on the next slide. In the later case, in the case of silica fumes, self-desiccation may occur to some extent even if water supplied during curing process, because the external water cannot easily are usually masked by the expansion associated with the formation of ettringite or the hydration of the free magnesium oxide. Okay, so it is significant in some cases, but it will be mostly masked by other phenomena. Okay, so as you can see here, the dependence of the autogenous shrinkage on water cement ratio. Look what happened here when we dropped from 0.3 to 0.2. Basically the internal, the relative humidity of the hydrating concrete or cement paste will be dropped. Okay, and here is the effect. Basically we will show what happened when silica fume is added. So look at the case here. This is both for water cement ratio 0.2. This is 0 silica fume added. We have 90% relative humidity measured. Look what happened when we add silica fume. The internal or relative humidity is 75%, and you see the amount of shrinkage, how it increased. Okay, so basically this is the case. And again, I mean, this is really not phenomenon to worry about in normal cases, but nonetheless it's good to be aware of it. Okay, the next topic is the carbonation shrinkage. As we have mentioned before, hardened cement paste will react chemically with carbon dioxide. The amount present in the atmosphere, about on the order of 0.04%, is sufficient to cause considerable reaction with the cement paste, but over a long period of time. However, this will result in irreversible shrinkage, and that's why it's called carbonation shrinkage. The extent to which cement paste can react with carbon dioxide and eventually undergo carbonation shrinkage is a function of relative humidity, as I will show on the next slide, and basically it is greatest around 50% relative humidity. At high humidities, carbonation is low basically because the pores are mostly filled with water and the CO2 cannot penetrate into the paste very well. At very low humidities, an absence of the water films is believed to lower the rate of the carbonation. That's what I have gathered, okay? Also, the carbonation shrinkage is greatest when carbonation occurs after drying rather than during drying, except of course for low humidities. So the concrete exposed to carbonation loses water and behaves as though it has been dried to a much lower relative humidity than that to which it is actually exposed. Okay, so the shrinkage water loss relationship is similar to that observed for normal drying. Also, the carbonation shrinkage is wholly irreversible, as I mentioned. It is believed that the carbon dioxide reacts with the calcium silicate hydrate and basically inducing a decrease in the calcium to silica ratio, and in parallel also loss of water or moisture. Okay, as you can see in this equation right here, second equation. Okay, so the carbonation of the calcium silicate hydrate is known to change the bonding characteristics of the material, which could account for their irreversible nature of the accompanying shrinkage. So carbonation can be viewed as promoting changes in the calcium silicate hydrate that normally only occurs at much lower relative humidity. Okay. Also, the calcium hydroxide will form calcium carbonate by reacting with the atmospheric calcium dioxide, as you can see in this equation right here, first equation. Okay, so the carbonation shrinkage can be important from a practical point of view. Advantage, there is always an upside, sometimes, not always, sometimes. An advantage can be taken of its irreversible nature, for precast concrete elements. Maybe just for CMU blocks. For example, by exposing the concrete blocks to calcium dioxide rich air, basically to expedite the carbonation process. The block can be made much more dimensionally stable to subsequent wetting and drying. Okay? But on the other hand, carbonation can be detrimental to cast in place concrete. So since it's much less porous than the block, for example. Carbonation can occur only near the outside and precisely where the maximum rate of drying is also occurring. Okay, so carbonation shrinkage is likely to be maximized, and when added to drying shrinkage may cause severe shrinkage cracking. Okay, so that's something of importance, and I am hopeful everybody when selecting or when designing a structure or trying to select material or mitigation measures to be also aware of this phenomenon. Okay, so let's look at the slide I just mentioned about how carbonation shrinkage is impacted by relative humidity. If you look at this graph, we have here the length change in percent, of course, increasing. I mean shrinkage, but the value is increasing as we go this direction, and this is the relative humidity. And you see here shrinkage, this is due to drying. Okay, and of course, basically it increases with the decrease in relative humidity. If you look at this, for example, right here, this is shrinkage due to simultaneous drying and carbonation. And again, almost the same. It increases with the decrease in humidity. For shrinkage, due to drying and subsequent carbonation, as you can see here, that it is greatest basically at a relative humidity of 50%. Okay, and we explained why. We said, worst at 50%, below 50%, the rate of carbonation is low due to lack of water. Above 50%, the presence of water slows the ingress of the carbon dioxide into the concrete. And these are the explanations I just mentioned during the discussion in the previous slide. Okay, so I will stop here for this topic, and we will continue next time. Next time we will discuss creep and the factors that affect creep. Maybe that also I will try to do it in one lecture. Maybe it will be too long, but I'm just trying to finish the subject in one lecture. So until then, thank you for watching, and I will see you next time. Thank you.